Okay, for this session, we're going to talk about large-scale structure in the universe. This is how galaxies and clusters of galaxies and superclusters of galaxies tend to cluster together. We're going to, again, some of these topics we're going to just do very briefly, but you can make careers out of studying each of these individual topics. We are really just given a very, very brief introduction to a lot of these topics. There's a lot more detail that you can go into. So again, if you have, questions about this, please, reach out and ask about those. So we talked about very early on in the course about our kind of location in the universe and some of these structures. We've got our planet, the Earth, is orbiting around the sun in our solar system. Our solar system is just one of hundreds of billions of solar systems that are orbiting around in the Milky Way galaxy. Our Milky Way galaxy is part of our local group of galaxies, which contain Andromeda Galaxy and a few dozen other smaller galaxies. We are on the edge of this Virgo Supercluster of galaxies. And that is just one supercluster that we see in a whole universe that's full of these clusters and superclusters of galaxies. So we're going to talk about this in a little bit more detail. This will also tie in when we talk about galaxy formation briefly. But let's look at some of these structures. We are in our local group has three large members of the group: the Andromeda Galaxy, spiral galaxy, our own Milky Way galaxy, again a spiral galaxy, and the Triangulum Galaxy. But there are a few dozen other smaller galaxies that are kind of all orbiting around each other in our local group. So we've got dozens of smaller galaxies, orbiting around the three larger galaxies. Again, the three larger galaxies being the Andromeda Galaxy is probably a little bit bigger than the Milky Way Galaxy. Triangulum is a fair bit smaller than the other two. But we've got lots of these other galaxies kind of orbiting around us. And this is fairly typical for galaxies. It's very rare that we find galaxies that are just isolated completely on their own. Kind of similar to how it's very rare that we see stars just sitting on their own. Stars generally form in clusters. Same thing with galaxies. So again, our local group has about 47 galaxies spanning a distance of about 10 million light years. Again, the largest ones being M31. M31 is the Andromeda Galaxy. M33 is the Triangulum Galaxy. There are other smaller galaxies. We don't have an image of our own galaxy like this because we are inside of the Milky Way galaxy, and we don't have the technology to send a camera far enough to get this kind of image of our own galaxy. We see lots of other galaxy clusters. This is the Fornax cluster. Let me zoom in on this so you can see some of these images a little bit better. This Fornax cluster has about 58 galaxies, and it's around 60 million light years away from us. Again, a few larger galaxies with many smaller galaxies orbiting around that. In the Coma cluster, this is around 320 million light years away. This galaxy cluster has over 1,000 galaxies inside of it. Again, the Hercules cluster, this is 100 galaxies, and this is about 650 million light years away from us. So again, we don't really see individual galaxies just kind of sitting out there on their own. So let me write down that particular point. So we generally see galaxies in clusters. In smaller groups, or larger clusters. And again, the smaller groups, our local group would be considered a smaller group. It's got a few dozen galaxies in it. Some of these other clusters contain thousands of galaxies. Some of the superclusters we're going to be talking about can contain many thousands of galaxies. So this is part of the, this is a diagram trying to represent the Virgo Supercluster. This is highlighting about 150 galaxy groups with an approximately 100 light years, sorry, that should be 100 million light years of us. So on this scale, this is about 10 million light years. These circles, the larger the circle, the more galaxies are in that particular group or cluster. So we would be located right at the middle of this. This is kind of the central part of the Virgo Supercluster, and we're kind of right on the edge of this Virgo Supercluster. Again, the isolated galaxies are pretty rare. We just don't really see those happen very much. They're generally in these smaller groups of a few dozen galaxies to larger groups containing thousands of individual galaxies. Notice there are also large regions where there are almost no galaxies. We call these voids. So let me write that one down. So you see some regions large regions with few to no galaxies are called voids. And again, we have what we call the local void. On this map, it would be just above us. On this map, we have this local void where we don't see many galaxies at all. This is trying to again represent this Virgo supercluster. It is a little bit difficult, partly because this is supposed to be a 3D representation, and having a 3D representation with depth on a screen, on a two-dimensional screen, is kind of hard. So it's kind of hard to see exactly, get like depth perception. But we do still notice there are areas where more galaxies are clustered in certain areas, other regions where we see very few galaxies. So again, these are the brightest galaxies in that same Virgo supercluster. If we zoom out, this is looking at the universe on an approximately 1 billion light year distance scale. So on this scale, we see that space is kind of clumpy. Galaxies and clusters and superclusters of galaxies tend to bunch up in some areas, and we get large voids in other areas. So let me write this down. So on around 100 million light year scales, galaxies tend to clump together. Down a little bit on this. Galaxies clump together, so we get some areas with clusters, some areas with clusters and superclusters, and some areas with voids. Again, notice on this scale, this is the Virgo supercluster. We are just on the very edge of that Virgo supercluster. There are other superclusters all mixed in here. We've got some areas that are voids where we don't see many galaxies at all. And again, this is trying to do a 3D representation on a 2D screen, so we do lose a bit of that depth perception. But again, on these 100 million light year scales, space seems to be clumpy. But if we zoom out even more, if we zoom out to even greater distances, and this is something called the 2DF Galaxy Survey. This is looking in two directions, spanning about 4 billion light years. on scales larger than about 1 billion light years, the universe kind of looks the same. We get the same kind of filament style, connections of all these galaxy clusters and superclusters. So again, on this larger scale, so on greater than 1 billion light years, so 1,000 million light years scales, the universe looks relatively the same. With these kind of spiderweb filaments of galaxy clusters and superclusters, so kind of like a spiderweb, like groupings of clusters and superclusters. But if I take that idea, if I were to pick, say, a random section over here, and I'm looking at this kind of a scale, it looks pretty much the same as a random section over here, or as a random section over here. Again, all of these different regions, if we look on a very, very large scale, they have pretty similar characteristics. And again, this is going to, tell us some things about the early stages of the universe, galaxy development, the development of clusters of galaxies, things like that, on these very, very large scales, more than 1 billion light years to a side. On those scales, it looks pretty much the same. One last thing, or a couple last things about this. Notice that this survey is only looking in 2 directions. We might want to ask, why was this survey just looking in one direction on the sky, taking a whole bunch of data from that one direction on the sky, and then looking in the exact opposite direction on the sky? Pause the video and see if you can think of why that is the case, or why that might be necessary. If from our vantage point here in the Milky Way galaxy, if we're trying to study other galaxies, why might there be 2 directions to look in where we're going to be able to get this data more easily? So pause the video for a second and see if you can answer that. So this point that I'm making of there's these 2 directions that this survey seems to have been taken in. And it's important to remember that when we're doing these surveys, we are inside of the disk of the Milky Way galaxy when we're trying to do these surveys. If we have our Milky Way galaxy, let me just do a quick little diagram of the Milky Way galaxy. We've got the bulge in the middle, we've got the disk, and we are living in the disk about 2/3 of the way out, right about there. Again, think, why might there be certain directions where it's going to be easier to take this data to do these surveys? Well, basically, in this case, if we're looking straight out of the disk, say up that direction or down in this direction, then we're not going to have the difficulty of having to look through all of the gas and dust in the disk of the Milky Way galaxy itself. We actually don't know a huge amount about the far side of the disk of the Milky Way galaxy. We don't have very good maps of that side of the galaxy. In fact, there are some smaller galaxies, some smaller dwarf galaxies that are on that side of the Milky Way galaxy that were only detected in the last few decades, because they're so hard to measure. Because in order to measure something over here, we have to look through all of the gas and dust in our own Milky Way galaxy in order to try to image those objects. This is why a lot of these surveys prefer saying, let's look directly above the disk of the Milky Way galaxy and directly below the disk, because that's going to give us the best measurements of these different parts of the galaxy. Though, of course, we are continually trying to get more and more data, looking at a wider a wider sampling across the sky to look at the entire universe. So lastly, when we run computer simulations of what the Big Bang would have been like, the very earliest phases of our observable universe, when we run computer simulations of the mechanisms that we think were going on during the early phases of the universe, the results of those computer simulations look very similar to the large-scale structure that we see in these kinds of surveys. Again, this kind of spider-webby looking grouping of galaxy clusters and galaxy groups, all kind of like that are interacting with each other on local scales. We have areas where there are voids. Again, when we talk about the Big Bang Theory and some of the evidence for the Big Bang Theory, we're going to see that computer simulations of what would have happened after the Big Bang match reasonably well with surveys that we've taken of these galaxies and looking at these larger scale structures. Again, we're going to be going into more detail on the Big Bang a little bit later in the course. Right now, we're just going to kind of finish with this saying we see galaxies in smaller groups and larger clusters. We don't really see galaxies that are just isolated. We see some large regions where there are no galaxies at all. We call them voids. On 100 million light year scales, we see that space is clumpy. There's regions where there's lots of galaxies in some areas, regions where there's very few galaxies in others. But if you zoom out even more to the billion light year scales and larger, on those scales, that spiderwebby looking filament of galaxies that we find, those seem to have similar properties as we look from different regions to each other. So we'll talk about how galaxy formation kind of works into this as well and supports some of these results, but we'll talk about that in some of the next sessions.